Bases. So with the language of linear independence at our disposal, the world is our oyster. There's all sorts of cool stuff we can do. So what is a basis? A basis is a particular type of list of vectors that live in whatever vector space you care about. So bases have two axioms. We call a list of vectors beta equals v1, v2 up to vd a basis for our vector space if two things happen. The first thing we need is what I like to call the spanning axiom. This means whatever space we care about is equal to the span of this list of vectors. Don't be intimidated by this equation. All this is saying is that whatever space we care about is comprised of vectors that are the linear combinations of whatever list we're interested in. The second thing we need is linear independence. We need our list of vectors to be linearly independent. Now, that was what the last lesson was on. If we have a list of vectors and we want to check whether or not it's linearly independent, the quickest way to do this is to put those vectors into the columns of a matrix and check that that matrix has nullity 0. And if you want intuition for what bases are, we think of bases as like a minimal spanning set. So the idea is that you might have a big list of vectors that spans your vector space, but you might have dependencies among those vectors in the list. So if you throw out the vectors that depend on the basis vectors, then you get a minimal number of vectors that span your space. Okay, so let's see an example here. Here, we're defining a vector space V as the span of this list of 3 vectors. Now, let's take a close look at these 3 vectors and see if there's anything intelligent we can say about them. Well, if we look at the first vector, it's 1, 2, 3. So this is a vector in R3. And if we look at the second vector, it's 2, 4, 6. Well, that's related to the first vector. This second vector is twice the first vector. And the third vector on the list is -1, -2, -3. That's -1 times the first vector. So we can imagine some geometry here. Let's say that I just represent the first vector as an arrow. The second vector on my list is 2 times that first vector. So geometrically, it's represented like this. And the third vector on the list is negative the first vector. So it's the same vector, just pointing in the opposite direction. And what is the span of this list of vectors? Well, the span is all linear combinations of the vectors in this list. But really what we're doing is we're just taking all multiples of the first vector. I didn't even need the second 2 vectors on my list to preserve the span. So V looks like this, some line parallel to the first vector in 3 space. So these vectors are dependent. The second vector is twice the first, and the third vector is negative the first. But if you choose any one of these vectors, now you have an independent list, and you haven't changed the span. So if you choose any one of these 3 vectors, you get a basis of V. So V could be viewed as the span of the first vector in the list, but that's the same as the span of the second vector because the second vector is a multiple of the first vector. And that's the same as the span of this third vector, again, because this third vector is a multiple of the first vector. So this is our first example of a basis. This V is defined as the span of this list of 3 vectors, but we didn't need all 3 vectors to define V. We only needed one of the 3. And one consequence of this example, which I think is interesting, is when someone gives you a basis of a vector space, keep in mind that there are many other bases. In general, there are infinitely many bases for a vector space. So you might find a basis for a space, and I might find a basis for a space, and you and I could totally have valid bases, but they might be completely different. Now, think about where we've seen situations like this before. If we're looking at the null space of a matrix, we need to solve the equation matrix times V equals the 0 vector for V. And the way we do this is by applying our theory of free and dependent variables. We identify the dependent variables and use the equations in the reduced row echelon form to write the dependent variables in terms of the free variables. So an example like this, maybe the matrix A I'm interested in is this 3 by 4 matrix. And when I row reduce this matrix, I find that the rank is 2. So I get 2 dependent variables and 2 free variables. Here the free variables will be the third and fourth variables. So I call those C1 and C2. And I use the reduced row echelon form to figure out how the dependent variables, which are the first 2 variables, relate to the free variables. And every time I do this, I always take one step further. I write the general solution vector where I've replaced the free variables with new labels, and then I write the generic solution as a linear combination of vectors. Effectively, what we're doing here is we're training ourselves to think in terms of linear combinations. What we've effectively done is we've shown in this example that the null space of this matrix is the span of this list of 2 vectors, -3, 1, 1, 0, and -16, 7, 0, 1. And this list of 2 vectors is linearly independent. So this gives us a basis. And people often call these the pivot solutions to AV equals 0. So if you go through this process of finding the reduced row echelon form and then writing out the generic solution as a linear combination of vectors, we call the vectors that pop out of this process the pivot solutions to AV equals 0. And it turns out this will always give a basis of the null space. So we call this the pivot basis of the null space of a matrix.